Alright, welcome back. In this video, I'm going to go over directional derivatives and the gradient. So, the directional derivative and gradient is a basic but important the concept in the vector calculus. Please listen carefully. So, we're going to figure out the not only the how to find the directional derivative and gradient, but also uh, we're gonna figure out the meaning of directional derivative and gradient. To do that, we gonna try to figure out the answer for two questions. First one is suppose you are standing on a surface and you walk in a direction other than x and y coordinate direction, then what is the rate of change of function in such a direction? Okay. The second question is, suppose you are standing on a surface and you release a ball at your feet and let it roll. In which direction will it roll? Okay, so the these questions will be answered in this video, and then while just trying to find out the answer for the questions, I'm going to introduce the directional derivative and then the main concept. I mean, the basic concept of vector calculus, which is the gradient. Okay, so just take a look at the graph. This is surface is given, which is the graph of the a multivariable function z equals f of x comma y, and we want to find out we can find out the slope of the tangent line of the curve along the x-axis, which is this. Sorry, this is y-axis. Okay, and then this is a curve along the x-axis. So it's not a big deal to find out the slope of tangent line at any point on this curve and that curve. But the what about so uh, the curve on not along neither x or the y-axis. So for example, let me see. I'm sorry, this one. That is the curve not along the x nor y. Okay, so that's the curve along the x-axis. This is a curve along the y-axis. I'm sorry about that. Okay, so then we can say these two curves are just are in intersection of, for example, this one is the intersection of the surface and the xz plane, which is the vertical plane. Um, the kind of we cut the surface using the xz vertical plane. Okay, then we're gonna get that curve. Okay, this one is also we can say that this is intersection of the surface and the yz plane. Okay, so anyway, so the goal is to here I want to find out the slope of tangent line along that curve. Okay, so let's see. To figure out that slope of tangent line, first we set up the surface, okay, and then the curve. Okay, so this is a curve given. Okay, so whose equation is z equals f of x comma y, and and then we want to find out the slope of the tangent line of the curve, but this curve is obtained by the cutting the surface by the vertical plane containing that vector. Okay, see, so the vector, let's say this vector is given. Okay, so that this curve has the same direction as the when you just project this curve on the xy plane, then the direction of the line on the xy plane, which is a projection of this curve, gonna be exactly same as the direction of that vector. Okay, so And then let's say this vector is a unit vector, which means that the magnitude of that vector is 1, and then components of that vector be u sub 1, u sub 2, and then this one is a curve, which is, I told you, intersection of the vertical line containing that vector and the surface. Okay, and then the point, and here then the whose x and y coordinates are a and b, then a comma b comma f of a comma b, that's going to be coordinates of the point on the curve. And then we want to find out the slope of the tangent line. See here, the line, let's say this is let's put the name for that line is L. There's a tangent line of the curve C at a comma b comma f of a comma b. Okay, so now you can see that then what the curve is not along the x-axis but nor y-axis, but the curve is along the that vector direction of this vector. Okay, so the slope of the tangent line. So the slope of tangent line L is called the directional derivative of f at a comma b in the direction of u, which is unit vector, right? And then that one determine the direction of the curve, which means okay, and denoted by this one d, capital letter D. And then here's to get the subscript vector u, and then f of a comma b. Okay, and defined by limit of this f of a plus h times u sub 1 comma b plus h times u sub 2, and the minus f of a comma b over h. And this one this one is can be obtained by the dot product of the partial derivative vector of partial derivative and the vector u. Okay, so that the this vector consisting of each component consists of the partial derivative is called the gradient. Okay, that's the notation of gradient. Okay, and then why this is equal to this, the proof is in the other lectures video. Okay, please watch that if you wonder why the directional derivative of f in the direction of u, vector u, is can be obtained by this. Okay, please watch that video. Okay, in that video I proved that. So, but in this video I'm gonna go over why this is defined by this. So definition of directional derivative is this, and then that's the theorem. Okay, so that we don't need to evaluate limit to find out directional derivative. Okay, we just find out the gradient, and then we're gonna compute the dot product of the gradient and the vector u. So okay, look at this. Why this is defined by this is it's quite simple. Okay, so strategy is the here's a strategy. We want to find out the slope of a secant line, and then we gonna limit the slope secant line so that to find the slope of tangent line. Okay, so here look at this. Let's say this is the surface. What we saw in a previous screen. Okay, so and let's say Q naught is the point whose components is a and b, and coordinates are a and b and f of a comma b. Okay, and we want to find out, the goal is to find out the slope of tangent line at Q naught. Okay, but we find out that one by finding the slope of secant line. Okay, so we just pick the Q. Okay, so now let's figure out the coordinate of Q. To do that, we just figure out the coordinates on the xy plane. Okay, so project the Q naught on the xy plane, then we get the a comma b, right? Let's say this is point P naught. Okay, and then this is the direction vector u. Okay, and then this is unit vector. Okay, u1 and u2, right? Right, okay, so now we're going to express the point Q, the coordinates of point Q in terms of components of vector u. Okay, since the components of vector u is u1, u2, if you just elongate vector u, okay, then we get the point P whose xy coordinates are exactly the same as the xy coordinates of point Q, right? Okay, because the direction of u exactly the same as the direction of the line, right? This the secant line, right? Okay, so because this core, you see that core, the projection of this core must be what the direction of the direction of the projection of this core on the xy plane must be exactly the same as direction of vector u. Okay, so let's say this is the length point P not to P is h. Okay, then that's gonna be h u1 h u2, right? By Pythagorean theorem, this is obvious, right? So the coordinates of P gonna be a plus h u1 and b plus h u2. It makes sense, right? So okay, now what are you gonna do? Then the slope of secant line gonna be what? We find out change f values, right? Which means that f of a plus h u1 comma b plus h u2, right? Minus f of a comma b. That's the change in kind of z value, right? Divided by h, right? That's the slope of the secant line, right? Okay, so now then we gonna take limit of that secant line, slope of the secant line, and that's gonna be slope of tangent line. So I define the directional derivative. Okay, so in general, the directional derivative of f in the direction vector u, which is d sub u and vector u of f, is the combination of f of x and fy. Right? You see? Okay. So why? Because so here I told you what from here in the theorems what because the directional derivative can be obtained by dot product of the gradient vector u. So that's why we can say that the in general directional derivative is the combination of the partial derivatives. Okay. So yeah, now finally we found the answer for the question one. Okay, so directional derivative. So in the second question is this: suppose you are standing on a surface and you release a ball at your feet and let it roll, and which direction it will roll? So to figure out the answer, we need to figure out the gradient. Okay, so let me introduce gradient. So gradient of f at x comma y is a vector value function. So keep in mind this gradient. The output of gradient is what? Vector. Okay, and then components of the gradient are the partial derivatives. So gradient f gonna be fx fy. Okay, and then using the basis vector, we can express gradient as like this: the sum of the fx vector I plus fy f sub y in the vectors basis vector j. Okay, and then in 3D, also gradient f can be expressed as like this. Okay, so but let's you know let me just remind the direction derivative f can be expressed as this, can be obtained by this, right? We see that, right? We saw that in the previous screen. So that let's figure out. Okay, it's finding the gradient is not a big deal. Okay, just find the partial derivative for given the equation of function. You find out the partial derivative of f with respect to x and y, but or in z in three-dimensional space, and then do dot product. Then you can find direction derivative, or just you can just find out the gradient. Okay, but what's the meaning of the gradient? This is really important to know before studying further in vector calculus. Okay, so look at this. Directional derivative f is this, and then using the what definition of dot product, this one can be expressed as like this: the magnitude of the gradient times the magnitude of the vector u times cosine theta. But since the vector u is a unit vector, so magnitude of vector u is 1. So it turns out that this one is equal to that. Okay, what is theta then? What? Okay, theta is the angle between direction vector u and gradient, right? So if theta equals 0, which means that the gradient and direction vector u has the same direction, then directional derivative is gonna have maximum value, because the maximum value of this one, we're gonna get this maximum value of this when theta equals 0, when cosine theta is 1. But theta equals 0, we're gonna get the 1, right? Well, I know theta is a 2 pi, or so we get the we're gonna get the cosine theta 1, right? But the cosine theta equals 2 pi, then we're gonna still have the same direction as the gradient vector u, right? All right, so it means that the directional derivative of f in the direction vector u has its maximum value, and f has its greatest rate of increase when gradient and vector u points in the same direction. Okay, and then second one. Okay, so maximum value. What's the maximum value then? Maximum value is nothing but what? The magnitude of gradient f. Okay. So when we're gonna get the maximum rate of change, rate of increase in the direction vector, that gradient has the same direction. I mean, gradient f and the direction vector u point in the same direction. Then we'll get the maximum, the rate of increase. Okay. On the other hand, well, if the two guys, gradient and then direction vector, as the opposite direction, completely opposite direction, so that theta is the pi 180 degree, then we'll get the greatest rate of decrease. Okay, so keep in mind this. So here's the example. Okay, so f of x is defined by 3x squared minus 2y squared. So this is the hyperbolic the paraboloid. Okay, so if you don't know what it is, please just search it. Okay, so compute the gradient f and the x comma y and the gradient f 2 comma 3. That's the it's not a big deal, right? We find out partial derivative with respect x and y, which is 6x and the negative 4y respectively, and then just substitute 2, 3 into xy, then you're going to get this. So now then find the second question. Find the theta gives the maximum and minimum value of directional derivative at 2, 3. Okay. So and then what angle of theta give us the maximum and minimum value of directional derivative at 2, 3? That's the question. So what are you gonna do? So we just gonna draw the lever curve. Okay, what's a lever curve? Lever curve is the graph of function, multivariate function, whose the which is the set of all of x comma y, the points x comma y, whose z coordinate fixed as constant. Okay, so which means that every single point on the lever curve, okay, their corresponding z coordinate is fixed as constant. Okay, that's the lever curve. So what are you gonna do? Yeah, so this, let's say this is a lever curve f passing through 2, 3. So when x is 2, when y equals 2, we get this the constant for z value. Okay, so all other points on the lever curve, when you plug them into the xy in the function f, we'll get the same value of z as the z value at 2, 3. Okay, so now let's figure out the the angle theta. Let's see. Yep, here. When the del angle theta the vector 12 comma negative 12. Why? Because we know that the directional derivative has the maximum value at the when the two guys have the same direction, and then its maximum value is the magnitude of gradient, right? So we'll find out the angle at this vector, okay? So 12 comma negative 12, let's say this is x and y, okay, coordinates. The 12 comma negative 12 may be right there. Then we find out theta, which is 7.4, and the magnitude of gradient at 2 comma 3, which is approximately 17. So we know that that 17 must be maximum value of directional derivative at 2 comma 3. Okay. So and then we just this is this is a position vector of that vector. Okay. So this is the what must be the direction of not only the gradient but also direction vector u, because when both guys have the same direction, we'll get the maximum value of direction derivative. That's so that what when angle is empire 4, which means that direction the angle of direction vector is empire 4, we get the maximum directional maximum the rate of increase, and then each maximum value is this 70. Okay, but see actually what and then alright, and then when in that direction, which is completely opposite to that direction, which is theta is 3 pi of 4. It's not a big deal. It's not a big deal to find out the angle of theta, which is the completely opposite to that direction, right? So the when theta is 3 pi of 4, we get the greatest rate of decrease. Okay, so then what's the minimum value of directional derivative? Negative 17, definitely. Okay, so now and there also when theta is a pi of 4 and pi of 4, which means that you see that those two vector, okay, these two vector, that's the direction orthogonal to gradient f of 2 comma 3 and then minus gradient f 2 comma 3, right? So it means that what? You see, it means that directional derivative must be 0, because if the direction vector u is this or this, then the directional derivative, since directional derivative can be obtained by the dot product of the gradient and the vector u, but if two vector u and the gradient is orthogonal, the directional derivative must be 0, is it? So when theta is pi 4 or pi over 4, then the direction derivative must be 0. Okay, so now then you see that here. So these two actually these are tangent vector, right? The tangent vector of the level curve, and they see that this is orthogonal, which means that orthogonal to the tangent vector, right? So now here we can see that directional derivative has the maximum value when the direction u is orthogonal to tangent vector. Is it true always? The answer is yes. Here's a theorem: the gradient of the level curve. So for the given function f, the line tangent, you see that here, this is level curve, okay? And then this is a tangent line, right? And then the gradient f, a comma b, if gradient direction of gradient f a comma b, gradient the gradient f a comma b is orthogonal to the level the tangent to the level curve, or we can say tangent vector. Okay. So now you see that? Okay. So then how come? So yeah, I proved that theorem in another video. So please watch that video. Okay. And then let's figure out the tangent line then. Can you just figure out the equation of tangent line? The answer is yes. So we're gonna use the fact the gradient f a comma b dot direction vector u direction vector v is equal to 0. Okay. That this is tangent vector. Sorry, tangent vector v equals 0. So v is the vector on the tangent line. So we can say tangent vector. So vector v, then the vector v can be expressed by x minus a comma y minus b. And then here x comma y is a point on the line. Okay. And then so we're gonna compute the dot product. Then we're gonna get this. The right hand is 0. So that's the equation of the tangent line. Okay. So keep in mind that the gradient f in the tangent line under the level curve is orthogonal, which means the perpendicular. So that the directional derivative has always has the maximum value when the direction vector u is the same direction as the gradient f, which is out normal. It's called that direction is called out normal. Okay, the direction which is orthogonal to the tangent line or tangent vector, that direction is called out normal. Okay, direction. All right. So the that's for today. Okay. So let me stop here.